Hello everyone, welcome back to our channel. I am Seema Shanay and today we are going to be looking at chemical analysis. This video includes explanation and solved problems on molarity, normality and different types of titrations with examples. Chemical analysis is the study of chemical composition and structure of substances. More broadly, it may be considered the corpus of all techniques whereby any exact chemical information is obtained. There are two branches in analytical chemistry, qualitative analysis and quantitative analysis. Qualitative chemical analysis is the branch of chemistry that deals with the identification of elements or grouping of elements present in a sample. It helps in the determination of the amount by weight of each element or compound present. The techniques employed in qualitative analysis vary in complexity depending on the nature of the sample. Quantitative analysis. To determine the amounts or concentration of substances present in a sample, chemists use a combination of chemical reactions and stoichiometric calculations in a methodology called quantitative analysis. Quantitative analysis combines chemical reaction and stoichiometric calculations to determine the amount of concentration of substances present in a sample. A primary standard is a reagent solution of accurately known concentration. A primary standard must have a known stoichiometry, a known purity or assay, and it must be stable during long-term storage. Therefore, a primary standard is made up of only those substances which are stable in ambient temperature conditions. A hygroscopic substance is one that readily attracts water from its surroundings through either absorption or adsorption. Examples include honey, glycerin, ethanol, methanol, concentrated sulfuric acid, and concentrated sodium hydroxide or lime. Because of the difficulty in establishing the degree of hydration, even after drying, a hydrated reagent or a hygroscopic material are usually not used as primary standards. A secondary standard is a chemical that has been standardized against the primary standard for use in specific analysis. Secondary standards are commonly used to calibrate analytical methods. They may be used for standardization. The base sodium hydroxide is an example of a secondary standard. Commercially available NaOH contains impurities of NaCl, Na2CO3 and Na2SO4 and readily absorbs H2O from the atmosphere. To determine the concentration of NaOH in a solution, it is titrated against a primary standard weak acid such as potassium hydrogen phthalate. Molarity M indicates the number of moles of solute per liter of the solution. Moles per liter, and is one of the most common units used to measure the concentration of a solution. Molarity can be used to calculate the volume of solvent and the amount of solute. To calculate the molarity of a solution, the number of moles of solute must be divided by the total liters of the solution produced. Solute is given in grams. We must first calculate the number of moles of solute using the solute's molar mass, then calculate the molarity using the number of moles and total volume. Molarity is equal to number of moles by volume in liters, which is equal to weight of solute by molecular weight of solute into volume in liters. Normality in chemistry is one of the expressions used to measure the concentration of a solution. It is abbreviated as N and is sometimes referred to as the equivalent concentration of a solution. It is mainly used as a measure of reactive species in a solution and during titration reactions, or particularly in situations involving acid-base chemistry. As per the standard definition, normality is described as the number of gram or mole equivalents of solute present in 1 liter of a solution. When we say equivalent, it is the number of moles of reactive units in a compound. Normality is equal to weight of solute by equivalent weight into volume, where equivalent weight is equal to molecular weight by H, where H is the number of reacting units. H for an acid is the number of H plus ions. For bases, it's the number of OH minus ions. Electrons in oxidation and reduction reactions, or valencies for ionic species. To find the normality of the acid and base titration, N1V1 is equal to N2V2, where N1 is equal to normality of the acidic solution, V1 is equal to the volume of the acidic solution, N2 is equal to the normality of the basic solution, and V2 is equal to the volume of the basic solution. A solution is prepared using 15 gram of sodium sulfate. The volume of the solution is 125 milliliter. Calculate the molarity of the given solution of sodium sulfate. The molecular formula for sodium sulfate is Na2SO4. The molecular formula for water is H2O. The molecular mass of sodium sulfate is calculated as M is equal to 23 into 2 plus 32 plus 16 into 4, which is equal to 142. The number of moles of sodium sulfate in the given question is calculated as N is equal to mass in grams by molecular weight, which is equal to 15 by 142, which is equal to 0.106. The volume of the solution is 125 milliliter. Expressing the above volume in terms of liters, volume is equal to 125 by 1000, which is equal to 0.125 liters. Now, using the formula, we calculate the molarity of the given solution as molarity is equal to number of moles of solute by volume of solution. Substituting the values, we get molarity is equal to 0.106 by 0.125, which is equal to 0.85 molar. Therefore, the molarity of the given solution is 0.85 molar. A solution of hydrogen peroxide is 15.2% by mass. What is the molarity of the solution? Assuming that the solution has a density of 1.01 gram per milliliter. Starting by assuming that we have 1 liter of the solution, hydrogen peroxide has a molecular formula of H2O2. Using the given density to find the mass of the solution, 1 liter into 1000 ml by 1 liter into 1.0 gram per milliliter is equal to 1010 grams. Next, to find the mass of hydrogen peroxide present in the given solution, 1010 into 0.152 is equal to 153.52 grams. Converting the mass of hydrogen peroxide into moles of hydrogen peroxide, 153.52 grams of H2O2 into 1 mole H2O2 by 31.04 grams of H2O2, we get 4.95 moles of hydrogen peroxide. Molarity is equal to moles of solute by liters of solution. Since we have 1 liter of solution, the molarity is 4.95 molar. What is the molarity of a solution in which 211 grams of sodium hydrogen carbonate is dissolved in 10 liters of solution? 211 grams of sodium hydrogen carbonate dissolved in 10 liters of solution has 0.251 molar. The first step is to calculate how many moles of NaHCO3 are present. 211 grams of NaHCO3 into 1 mole of NaHCO3 by 84.006 grams of NaHCO3 is equal to 2.51 moles of sodium bicarbonate. Molarity is equal to moles of solute by liters of solution, which is equal to 2.5 moles by 10 liter, which is equal to 0.251 molar. How many milliliters of a 5 molar copper sulfate solution are needed to prepare 0.350 liters of 0.5 molar copper sulfate? 35 ml of 5 molar copper sulfate solution is needed to prepare 0.350 liters of 0.5 molar copper sulfate. We can use the formula M1V1 is equal to M2V2. Therefore, 5 into V1 is equal to 0.350 into 0.5, which implies V1 is equal to 0.035 liters, which is equal to 35 milliliters. What is the molarity of a solution containing 750 ml of solution containing 35 grams of magnesium carbonate? Molarity is equal to moles of solute per liter of solution. We're given that there is 35 grams of magnesium carbonate and 750 ml of solution. We first convert the milliliters of solution to liters. 750 ml is equal to 7.5 into 10 square milliliters. 7.5 into 10 square by 10 cube is equal to 7.5 into 10 power minus 1 liters. Now we convert 35 gram of magnesium carbonate to moles to get moles of solute per liter of solution. This is done by dividing 35 grams by its molecular weight, which is 84.13 grams. 35 into 3.5 into 10 into 1 mole of magnesium carbonate into 1 by 8.413 into 10 is equal to 0.416 mole of magnesium carbonate. 4.16 into 10 power minus 1 into 1 by 7.5 into 10 power minus 1 liters is equal to 0.55 molar. Calculate the normality of NaOH solution formed by dissolving 0.2 gram of NaOH to make 250 ml of solution. Normality is equal to number of gram equivalents of solute by volume of solution in liters. Number of gram equivalents of solute is equal to weight by equivalent weight. Therefore, equivalent weight is equal to molar mass by N, which is equal to 23 plus 16 plus 1 by 1, which is equal to 40. Therefore, normality is equal to 2 by 40 into 1000 by 250, which is equal to 0.2 normal. Find out the volumes of two HCl solution, P 0.5 normal and Q 0.1 normal, to be mixed for preparing 2 liters of 0.2 normal HCl solution. Let Y liters of P and 2 minus Y liters of Q be mixed. N1V1 plus N2V2 is equal to NV. Therefore, 0.5 into Y plus 0.1 into 2 minus Y is equal to 0.2 into 2. 0.5 minus 0.1 into Y is equal to 0.4 minus 0.2. Therefore, Y is equal to 0.5 liters. Hence, 0.5 liters of A and 1.5 liters of B should be mixed. In the following reaction, calculate and find the normality when it is 1 molar H3PO4. H3ASO4 plus 2 NaOH giving Na2HASO4 plus 2 H2O. If we look at the given reaction, we can identify that only 2 of the H plus ions of H3ASO4 react with NaOH to form the product. Therefore, the two ions are two equivalents. In order to find the normality, we'll apply the formula N is equal to molarity into number of equivalents. N is equal to 1 into 2, replacing the values. Therefore, normality of the solution is 2. Calculate the normality of 0.321 gram of sodium carbonate when it is mixed in a 250 ml solution. Normality of 0.321 gram sodium carbonate, N is equal to Na2CO3 into 1 mole by 105.99 grams into 2 equivalents by 1 mole. N is equal to 0.1886 equivalents by 0.2500 liters. N is equal to 0.0755 normal. What will be the concentration of citric acid if 25 ml of citric acid solution is titrated with 28.12 milliliters of 0.1718 normal KOH? N1V1 is equal to N2V2. N1 into 25 milliliters is equal to 0.1718 normal into 28.12 milliliters. Therefore, the concentration of citric acid is 0.1932 normal. Find the normality of the base if 31.87 milliliters of the base is used in standardization of 0.4258 grams of KHP, equivalent weight 204.23. 0.4258 gram of KHP into 1 equivalent by 204.23 into 1 equivalent base by 1 equivalent acid is equal to 2.085 into 10 power minus 3 by 0.03187 liters, which is equal to 0.6542 normal. Therefore, the normality of the base is 0.6542 normal. What is the normality of the following 1 liter aqueous solution containing 80 grams of NaOH dissolved in it? Firstly, in order to determine the normality, we need to find the number of equivalents. For NaOH, the number of equivalents is equal to 1. Therefore, equivalent weight is equal to 40 grams. Therefore, number of equivalents is equal to given mass by equivalent mass. 80 by 40 is equal to 2 equivalents. Hence, N is equal to number of equivalents by volume in liters, which is equal to 2 normal. A titration is an experimental procedure in which a carefully measured amount of a solution of known concentration is added to a measured volume of a solution containing a compound whose concentration is to be determined. The reaction used in a titration can be an acid-base reaction, a precipitation reaction, or an oxidation-reduction reaction. The equivalence point, the point in a titration where a stoichiometric amount, that is the amount required to react completely with the unknown, of the titrant has been added, is reached when a stoichiometric amount of the titrant has been added. The amount required to react completely with the unknown. A titrant is a solution of known concentration that is reacted with a compound in a solution of unknown concentration in a titration. In all cases, the reaction chosen for the analysis must be fast, complete, and specific. That is, only the compound of interest should react with the titrant. The end point is the point at which the reaction is observed to be complete. It's a signal to stop adding more reagent and make the final reading of the burette. A pipette is for measuring accurate and precise volumes of the solution. A burette is used for pouring measured volumes of solution. Conical flask is used for mixing two solutions. Wash bottles contain distilled water for cleaning equipment. A funnel is to transfer liquids without spilling. Volumetric flasks is a flask used to make up accurate volumes for solutions of known concentrations. The different types of titrations include acid-base titration, complexometric titrations, redox titration, precipitation titrations, and double titrations. Acid-base titrations, acidimetry or alkalimetry. An acid-base titration is a quantitative analysis of acids and bases. Through this process, an acid or base of known concentration neutralizes an acid or base of unknown concentration. The titration progress can be monitored by visual indicators, pH electrodes, or both. The reaction's equivalence point is the point at which the titrant has exactly neutralized the acid or base in the unknown analyte. If we know the volume and concentration of the titrant at the equivalence point, we can calculate the concentration of the base or acid in an unknown solution. The primary standards used for an acid-base reactions are Na2CO3, KHP, succinic acid, benzoic acid, and oxalic acid. The procedure of an acid-base titration is as follows. The required volume of base is taken whose concentration is known in a pipette and is poured into the titrating flask. The acid whose concentration is unknown is taken in the burette and is allowed to react with the base drop by drop. An indicator which is used for detecting the end point is also added in the titration flask. When the reaction reaches completion, the color of the solution in the titration flask changes due to the presence of an indicator. The indicator used for this purpose can be phenolphthalein, which forms pink color in basic solution and is colorless in acidic or neutral solution. Therefore, the end point is detected when the pink colored solution turns colorless. Double titration. In this type of titration, the titrate of unknown concentration solution contains more than one component. For finding the composition of the mixture is to check the purity of a sample, titration of the mixture is done against a strong acid. But in this case, instead of one indicator, two indicators are used because there are going to be two endpoints during the titration. The commonly used indicators are phenolphthalein and methyl orange. An example for a double titration experiment is as follows. The estimation of the total alkalinity of water samples CO3 2- or HCO3- using double titration method. Sodium carbonate reacts with hydrochloric acid in 2 stages. Sodium bicarbonate reacts with hydrochloric acid in 1 stage by the second reaction. The first reaction, which is Na2CO3 plus HCl giving NaHCO3 plus NaCl, which is a half neutralization reaction, occurs at pH 8.5 and can be monitored using phenolphthalein as an indicator. The second reaction, which is NaHCO3 plus HCl giving NaCl H2O plus CO2, which is a complete neutralization reaction, occurs at pH 4.3 and can be monitored using methyl orange as the indicator. The procedure of the experiment is as follows. The given sodium carbonate and sodium bicarbonate mixture is made up to 250 cm³ in a standard flask and shaken well. 25 cm³ of this solution is pipetted out in a clean conical flask. 2 to 3 drops of phenolphthalein indicator are added. The pink solution obtained is titrated against the 0.05 normal HCl in the burette until the pink color disappears. The burette reading is noted and is marked as T1. To this colorless solution obtained, 2 to 3 drops of methyl orange indicator is added. The yellow solution obtained is titrated against the standard HCl in the burette until it turns reddish orange. The burette reading is noted again and is marked as T2. This two-step titration is repeated again for concordant value. Redox titrations. These types of titrations are almost similar to the volumetric acid-base titrations, except that here the reactions involved are redox reactions. Here the interest is laid upon finding the unknown concentration of a reducing or an oxidizing agent. The oxidizing or reducing agents are titrated against strong reducing or oxidizing agents respectively. In most of the redox titrations, one of the reactants itself will act as an indicator, that is a self-indicator, changing their color with respect to the oxidizing states. The 3 types of redox titrations are permanganometric titrations, iodometric titrations, and iodimetric titrations. The primary standards used for redox titrations are K2Cr2O7, potassium bromate, KiO3, sodium oxalate, and arsenous trioxide. The example of a permanganometric reaction is the estimation of oxalic acid by titrating it with standard KMnO4. The equivalent mass of oxalic acid H2C2O4.2H2O is half of its molecular mass, that is 126 by 2, which is equal to 63. To prepare 250 cm³ of 0.05 normal solution, 63 into 0.05 by 4, which is equal to 0.7875 grams of oxalic acid is required. This amount of oxalic acid is used to make 250 cm³ of its solution to obtain a standard solution. A known volume of the solution is titrated against the given KMnO4 solution to determine its concentration. KMnO4 is present in dilute H2SO4, generates nascent oxygen which oxidizes the oxalic acid to CO2 and H2O. The reactions are 2 KMnO4 plus 3 H2SO4 giving K2SO4 plus 2 MnSO4 plus 3 H2O plus 5 O. H2C2O4 plus O gives 2 CO2 plus H2O. Since 2 molecules of KMnO4 generate 10 equivalents of oxygen, its equivalent mass is equal to molar mass by 5, which is equal to 158 by 5, which is equal to 31.6. The procedure of the reaction of the titration is as follows. About 0.78 grams of oxalic acid is accurately weighed and completely transferred into 250 cm³ standard flask using a clean funnel. The funnel is removed and the flask is swirled to completely dissolve the oxalic acid. The volume is precisely made up to the mark, stoppered and shaken well. The normality of the solution is calculated. 25 centimeter cube of this prepared standard solution of oxalic acid is pipetted out into a clean conical flask. One test tube full of dilute H2SO4 is added to the mixture and heated till the appearance of the first bubble. The hot solution is titrated against KMnO4 solution taken in the burette, taking care to add the first few drops slowly. KMnO4 is a very good oxidizing agent and can oxidize oxalic acid into carbon dioxide and water. However, KMnO4 can behave as an oxidizing agent only in the presence of a mineral acid. KMnO4 releases nascent oxygen in the presence of a mineral acid. Nascent oxygen is a highly reactive species which actually oxidizes the given oxalic acid. The endpoint is indicated by the appearance of a pale permanent pink color. The titration is repeated for concordant values. Iodometric titrations. The term iodometry describes the type of titration that uses standardized sodium thiosulfate solution as the titrant, one of the few stable reducing agents where oxidation of air is concerned. Iodometry is used to determine the concentration of oxidizing agents through an indirect process involving iodine as the intermediary. In presence of iodine, the thiosulfate ions oxidize quantitatively to tetrathionate ions. To determine the concentration of the oxidizing agents, an unknown excess of Ki solution is added to the weakly acidic solution. The iodine, which is stoichiometrically released after reduction of the analate, is then titrated with a standard solution of sodium thiosulfate. An example of an iodometric titration is as follows. Estimation of copper 2 ions iodometrically using Na2S2O3. Copper is present in the solution as cupric ions. The solution on treatment with excess of potassium iodide solution liberates iodine equivalent to the amount of cupric ions. The liberated iodine is titrated against standard sodium thiosulfate. The sodium thiosulfate is standardized using standard potassium dichromate solution prepared. The equivalent mass of potassium dichromate is 49. To prepare 250 centimeter cube of a 0.01 normal solution, 49 into 0.01 by 4, which is 0.1225 grams of K2Cr2O7 is required. About this amount of potassium dichromate is used to make a standard solution. The reactions are as follows. CuSO4 plus 2 Ki giving CuI2 plus K2SO4. 2 CuI2 giving Cu2I2 plus I2. The procedure of the titration is, we accurately weigh the given potassium dichromate crystals into a 250 centimeter cube standard flask, dissolve it in water and make it up to the mark. We shake it well to obtain a uniform concentration. We pipette out 25 centimeter cube of the standard potassium dichromate solution into a clean conical flask. Add about 2 centimeter cube of concentrated HCl and 5 centimeter cube of 10% potassium iodide. We titrate the liberated iodine against sodium thiosulfate. Add 1 ml of starch indicator towards the end point. Add starch when the solution in the flask becomes pale yellowish green. We continue the addition of sodium thiosulfate drop by drop till the blue color is developed on adding starch. Gets just discharged. We repeat the titration for concordant titer values. Make up the given copper solution to 250 centimeter cube in a standard flask. Shake well and pipette out 25 centimeter cube of the solution into a clean conical flask. We add ammonium hydroxide drop by drop till a pale blue precipitate is formed. Adding diluted acetic acid till the precipitate completely dissolved. NH4OH is added in order to remove any mineral acid present. Add about 5 centimeter cube of 10% potassium iodide solution. We titrate the liberated iodine against sodium thiosulfate taken in a burette. Add 1 centimeter cube of starch solution towards the end point. The solution turns deep blue. We continue the addition of sodium thiosulfate drop by drop till the blue color starts to fade. We add 3 centimeter cube of 10% ammonium thiocyanate ions and continue the addition of sodium thiosulfate till the blue color just gets discharged. Complexometric titration or chelatometry is a type of volumetric analysis wherein the colored complex is used to determine the endpoint of the titration. It is sometimes termed as volumetric analysis as measurements of volume play a vital role. Complexometric titration is used in the detection of mixtures of different metal ions present in the solution. When each drop of titrant is added, the reaction reaches an equilibrium state swiftly. There would be no chance for any interfering situations. The equivalent point can be identified very accurately using a complexometric titration. EDTA is a commonly used titrant. Primary standards for this kind of titration include pure metals such as zinc, magnesium, and manganese and their salts. Precipitation titration. It is a titrimetric method which involves the formation of precipitates during the experiment of titration. The titrant reacts with analate and forms an insoluble substance. The titration is continued till the last drop of analate is consumed. When the titrant is excess, it reacts with the indicator and signals to terminate the titration process. An example of a precipitation titration is to determine the concentration of chloride ions in a certain solution. We can titrate the solution with silver nitrate whose concentration is known. The chemical reaction is Ag plus in aqueous plus Cl minus to give AgCl, which is a solid. AgCl in the form of a white precipitate can be seen settled at the bottom of the flask during titration. The quantity of silver ion used to equivalence point is equal to the quantity of chloride ion which is originally present. Some of the primary standards used for precipitation titrations are NaCl, KCl, KBr and AgNO3. If you have any doubts regarding the problems or the concepts that I've covered in this video, please leave your doubts in the comment section below. I will answer them to the best of my knowledge. Thanks for watching. Please like, share, comment and subscribe for more videos like this. Hit the bell icon to get notified every time I post.